Okay, let's start today's last session. The last speaker today is Rinat Kashaev. The title of his talk is Invariants of Surface Boundaries in Quantum Teichmüller Theory. Thank you.
Thank you very much. Thank you, Professor Murakami, for inviting me and giving the opportunity to talk at this conference. So my talk will overlap probably a little bit with the talk of Ray, which we had listened before the break. But I'd like to talk about a little bit more globally. In the sense that so quantum topology in the form of infinite dimensional representations which arise in quantum Teichmüller theory, for example, poses a problem in functional analysis. So let me just formulate what is this problem. So it is a question motivated by quantum topology. So the question is the following. So let A be a bounded operator in a infinite dimensional Hilbert space. In infinite dimensional Hilbert space. And then the question is the following: when one can make sense of its trace. And if you look at the functional analysis textbooks, then people, in order to define a trace of an operator, people immediately define a very restricted class of operators, which are called trace class operators. These are compact operators with a spectrum given by a sequence of complex numbers, which converge to zero sufficiently rapidly. The way that the sum of the eigenvalues converges absolutely. But quantum topology, we will see a little bit later that it provides with the problem of calculating traces of unitary operators. And unitary operators have their spectrum on the unit circle, and so if even if the spectrum is discrete, it is clear that the sum of eigenvalues is not absolutely convergent. It can be only, but for series we can speak about convergence without asking for absolute convergence. So the question persists. But let me just give a comment how an answer to this question would look like. How a general answer to this question would look like. And let me give one general answer, but it is not an answer, of course, but just some strategy of trying to answer such a kind of question. So let us take case of bounded operators, B of H. the whole set of bounded operators. And then in this set we have a subset of trace class operators. And here we have a function called trace, which is a linear form on that vector subspace, which associates to each element a complex number. And now let us choose a provide B of H with a topology, and let me put in the parentheses sufficiently weak topology. So that trace is continuous. Trace is continuous. Or bounded linear form. No, bounded is just if it is metric topology, but in general just a continuous linear map. And then what we can do, so we have a B of H, we have a subspace TC of H, and we have a map given by trace from TC of H, and now we can take a closure of TC of H, of H with respect to this topology, and then we can ask if we can extend this continuous function continuously to some part of the closure, right? And then if we can enlarge a little bit the trace class operators in this way, just by working with a given function and extending it as much as possible continuously to a larger domain, then that would be an answer to that question. Just a trivial example. Let us take a function on the real line without one point to real line given by sine of x divided by x. And then we can extend f. Then f continuously extends to the whole real line, right? Because we just add a point at origin unique value for the f, and we get a perfect continuous function on the whole line. So, but in this setting, we have an enormous space, not just real line, the space of bound operators, and a function which is continuous by this choice of the topology. And then we are looking for if we can add points like 0 for that function in the space of bounded operators, the way that the trace function still well defined and continuous. Okay, now let me just explain why this question comes from quantum topology. Why quantum topology? The reason is very simple. So assume that let ρ be a representation of the mapping class group of a surface into unitary, say, a unitary representation in a Hilbert space. And then, so we always, if we have a TQFT, then as a part of the theory, we always get a representation of the mapping class group, no matter which TQFT we take, right? But usually TQFT are underlined by finite dimensional vector spaces, so the representation is finite dimensional. But let us think about TQFT of infinite type. We know that there are such. Then we can ask if we can make sense of that representation as a part of a bigger theory which provides us with topological invariance. And then if such theory exists, then the topological invariance one would expect to be given, at least in the case of mapping cylinders, by the traces of the monodromies, of the images of the monodromies. Then the invariance, yeah. So then trace of rho of phi is expected to be a topological invariant of a mapping cylinder, which means that we take a surface, multiply with a unit interval, and coercion with respect to identification given by 0 is equivalent. No, how it goes? Phi of x 0 is identified with phi of x 1. Okay, so that's the mapping cylinder, and then and if we have a unitary representation, then we've got to make sense of a trace of a unitary operator, and that's why we get to this problem. Okay, now let me give an illustrative example. Why illustrative? Because this example is simple enough that we can go all the way through calculations. So what is this illustrative example? We take H to be L2 of R. L2 of R, and any quantum physicist, when sees L2 of R, immediately can think about Heisenberg operators. PQ Heisenberg's momentum position operators. So I define them just by explicit action. So P Q acts by multiplication, and the P acts by differentiation. But I choose a specific normalization corresponding to H bar equal inverse of 2 pi. And then we have the famous Heisenberg commutation relations. Like this. So these are self-adjoint but unbounded operators, and the derivative of a square integrable function should be understood in the sense of distributions. So in this sense, this operator can be applied to any element. So these are Heisenberg operators, and then we we can define a representation of the group, projective representation of the group SL2R, which is called metaplectic representation. So then we have metaplectic representation of the symplectic group, which is in this case will be just SL2R. Representation of SL2R. What is this? So we can define it just by two generating elements generated by E pi I alpha t squared and E pi I alpha q squared, where alpha is just a real number. So we take this two one parameter families of unitary operators. They are unitary explicitly, and then we just have to say in which sense this is a representation of SL2R. And the answer is given by the following formula. We take a joint action, say, of that guy, but I take a minus just to make a right order in the representation. I mean to get a representation, not anti-representation. Pi alpha p squared acting on a column of PQ Heisenberg pair. And then if you now we can use Baker-Kendall-Hausdorff formula to apply this action. So P commutes with P, so P will not change, but Q will be shifted, and it will be shifted by negative value of P. Okay, and this we can rewrite as an action of SL2R 2x2 matrix on the same column, like this: 1 0 minus alpha 1 acting on PQ. Just the usual action of 2x2 matrix to the column vector, and we get to here. But on the other hand, the same effect is achieved through conjugation by this quantum operator. So that means that this particular operator is associated to this particular 2x2 SL2R matrix. Likewise, for the second operator, we get this time, so this depends on Q, so Q will not be changed, but P will be shifted in the positive direction by alpha times Q, and again we can write this as a 1 alpha 0 1 acting on a PQ column. So the second operator realizes upper triangular matrix, and now any SL2R matrix can be factorized into 3 lower upper triangular matrices, so that we can generate any other element by taking products of such things, but of course varying alphas in different components. And yeah, so in particular, we can realize a subgroup, any subgroup of SL2R. For example, the subgroup of SL2Z, which is identified with the mapping class group of the torus. now in particular, one has a realization of SL2Z sitting inside the SL2R. And this is a mapping class group of S1 cross S1. Okay, so we get exactly to the situation which I was describing here. And to identify this representation of that subgroup, we just have to say what is T. Right? So we have T matrix and the S matrix. These are generating elements of SL to Z, and this goes to, if we look here, so we have to choose alpha equal 1. So this goes to I q squared. But for this guy, we have to split this matrix into product of 3, and I will not do this.
Why do you have to split it? I mean, SL2C is generated by T and by 1, 0, 1, 1.
Yes, but this is more standard.
No,
right? So
you don't have to split.
physicists will not like otherwise. So it will be this kind of I p squared, pi I q squared, e pi I p squared. So which means that I claim that what I do claim 1 0 minus 1 1 1 1 1 0 1 minus 1 1 0 should be equal. I hope the claim is correct. Okay, so that's the way how we get a representation of a simplest mapping class group, and now we can start trying to see if we can make sense of traces of those metaplectic operators.
Excuse me, do you have some ambiguities to the answer? I mean,
yeah, it is a projective. So this is why metaplectic, because metaplectic is a covering, double covering of the symplectic. And this makes sense for any L2 of Rn, because we can think of H1 of genus G surface. H1. First cohomology of a surface of genus G, and quantize it, and then we get exactly the metaplectic representation of SP n R.
I see.
Because it acts by symplectic morphisms, where symplectic structure is given by intersection of H1. And this is just the case in the torus case.
You said that it's taking a trace, so that means the trace will depend on this factor. I mean, which one?
The projective factor. Yes,
Yeah.
but up to phase, right? Now you can take absolute value, then you can think that absolute value could be invariant. But of course, this is not a way of constructing invariant. This is how we probe, right? We can expect that this, in the end of the day, if you manage to find justification why this is invariant, could happen to be invariant. But anyway, you have to try to make sense of its trace. That's my point. And so, as I remarked already, so all these operators are unitary. So even the spectra are discrete. The sum of eigenvalues will not be absolutely convergent in no way, because they live on the unit circle. But let us see anyway. Let us see what we can do.
Excuse me.
Yes.
So these operators have discrete spectrum, not continuous, not the whole circle?
No. But the spectrum of Q is a whole real line. So so T operator of course has a spectrum the whole circle. Yeah. So it is not even discrete.
Yeah.
But let me just take this. I can erase. Let us take another operator. Let rho alpha be this operator, E pi I P Q plus QP. And I take the symmetrized quadratic structure like this.
Alpha?
Alpha, yeah, alpha. Alpha, if we take this operator, then it can be, it lives in the same metaplectic group. And then if we try to act on PQ, then again, Baker-Campbell-Hausdorff formula will give us this. So in other words, it realizes diagonal matrices. Yeah, of course you can realize them as a product of three generating elements, but we can take just one new element which just acts explicitly by diagonal rescaling. And these matrices are nice, even if they are not in SL2Z. They can be conjugated to a mass of elements of SL2Z with a trace greater than 2. And then these are geometrically nice elements because they have a stretching factor, and so let us see if we can make trace of at least those operators. Okay, so yeah, so how to calculate the trace? So define, so any operator can be described by an integral kernel, by its integral kernel. Any operator A. Okay, so A acts on F. It gives a function, and this function we always can write like K A of xy, f of y, dy. And the kernel is the distribution valued object, which is the Schwarz theorem, actually. And then define trace of A as an integral of the diagonal of the integral kernel. Of course, if A is trace class, then this is just the way of calculating the trace, which is defined independently, say, as a sum of eigenvalues. But if A is not trace class, then we take it as a definition, working definition. So which coincides with the, so if you wish, this is kind of extension of the trace function to a larger class, or at least an attempt to extend it to a larger class. And let us see if we can get something out of this. So try to apply to rho alpha. What is rho alpha? Rho alpha eventually can be calculated rho alpha f acting on x. It's going to be f of yeah, we can of course make this exercise, but to save time, let me write the answer. X e alpha e to alpha half. So that's a way rho alpha acts on functions. And then, of course, we can rewrite it as an integral in terms of according to this formula, rho alpha of xy, f of y, dy, where k rho alpha of xy is given by e alpha half delta function of y minus x e to alpha. Just a very elementary substitution. And now what we have to do, if we want to try this definition, then we have to equate x to y. K rho alpha of xx is the e alpha half delta function of x. So y becomes x minus x some constant. So we can pull out x 1 minus e alpha. And this is constant. And those who know how to manipulate with the delta function will agree that we can pull out just outside in the denominator, but putting absolute value. And what remains is the delta function. So that's trace of rho alpha, according to our definition, is just a matter of integration of that function of x along the real line. But everybody knows how to integrate that function. So it is the e alpha half 1 minus e alpha absolute value. Or we can write it more symmetrically twice since absolute value of alpha half. So you see, if alpha is not 0, then we manage to get a finite answer. And even more, we know that rho 0 is the identity operator. And we know that identity operator in no way can be traced out with finite answer. And our formula confirms that if we try to put alpha equals 0, we get infinity. But any other value, non-zero value of alpha gives us a sensible answer. And even more, so we remark that the rho alpha can be written in the form I phi alpha d, okay, where d is just pq plus qp, self-adjoint unbounded operator. D and the spectrum of D is the whole real line. That's a simple spectral problem. So you have to deal with the first order differential operator in the coordinate representation, and easily solve. So actually, this spectrum is doubly degenerate. So for each real number, you have two linearly independent generalized eigenvectors. Yeah, so we have an example of a unitary operator which has a pure continuous spectrum, and nevertheless we managed to make sense of its trace. Of course, suppose we take some ad hoc definition for the trace, and the questions like if we take another representation of L2R, equivalent representation, will we get the same answer? Is open. So, but if one can make this result as a result of continuous extension of the trace function in the space of trace class operators with respect to some topology, with respect to which the trace function is continuous, the simplest way to choose the weakest topology with respect to which the trace function is continuous. There is unique such topology, and then one can try to extend continuously the trace function, and then if we are lucky, then probably this operator will find it in the extended domain of that function.
So I have two questions.
Yeah.
If the space is finite, then the trace is original usual trace. And if the space is finite dimension,
Yes.
and the operator is finite one.
It's a matrix, right?
Yeah,
Then
yeah,
it's a matrix. Yeah.
That definition is the.
No, but there will be no integration, right? Then
really?
integration will be a summation.
I see.
Then it will be sum of diagonal elements. So as a usual definition of the trace.
And if you extend the trace continuously, then the result still hold property of usual trace.
This I don't know. This I don't know. All these questions are open, right? So I mean,
Do you have any example of a sequence of trace class operators which at least look, since you don't know the topology, look like they're converging to raw alpha,
no problem.
and this trace does converge to this
Of course. Take just perturb this with a harmonic oscillator, exponential of harmonic oscillator with a small coefficient, then it will become trace class, negative coefficient, right? So if you take
actually that was going to be my other
minus
question.
epsilon harmonic.
Exactly. Well, that's my other question. If you just take the operator with e to the minus epsilon absolute value squared, that is trace class, and then look at those things where the limit exists when epsilon goes to 0.
Yeah, but then you have to make sure that if you choose another perturbation, that you will arrive to the same limit. That's yes, you are right. So that's a way of attacking the question, but difficult part to make sure that nothing depends on your choice. Exactly. Like with this sine x over x, no matter how you perturb, to make sense, you will end up with a value 1, right, at 0.
No, only if you use the usual real topology.
Yeah, of
If I
course.
use some other topology, I might get another answer.
But you have to make sure that the initial function was continuous on the exterior of the origin.
Exactly, yeah. So and you don't know even the definition of the topology, so it's a little hard to check anyway.
Yeah, so that's the illustrative example, and maybe just the last remark. The last remark on that is the following. So remember that what we expect if we try to topologically interpret the trace of rho alpha as a partition function on some hypothetical TQFT underlying this representation of the mapping torus, then we can look at what is rho power n. Then its trace should be n cyclic covering of that torus bundle. And but in our example, rho alpha power n is the same as rho n alpha, right? So so the trace of rho alpha n just becomes 1/2 sinh n alpha absolute value half. And then so the natural thing to try is to see what happens when the degree goes to infinity, and we observe nice exponential behavior here in the form of e to minus n absolute value alpha half. And so this is also instructive conclusion, because the theory is unitary, and the general principle in quantum physics is that in unitary theory you never have exponential growth, but you can have exponential decay as it happens in this example. And another thing is that we, by this asymptotic behavior, we just detect the stretching factor of the monodromy. Okay, now I switch to quantum Teichmüller theory. So, having done this exercise, we can try to see something less trivial. So, from that moment, I will overlap a little bit with Ray's talk. But of course, I have my own preferences in formulating quantum Teichmüller, so let me just sketch what I understand when I say quantum Teichmüller. Theory. So the story is about two unitary operators. So two unitary operators. So I use from time to time different notations. Let me choose this time operator R, which is unitary of L2 of R, and operator W, which is unitary operator in L2 of R squared. And yeah, so let me write. It will take some time, but everything is very explicit. So, for example, the explicit form of those operators is for R is 3 pi I q squared E pi I p plus q squared. So I'm using the same Heisenberg operators, and here's some little correction. E 2 pi I alpha p E pi I alpha squared minus 1 over 3. Alpha is just a parameter of the theory. Which is arbitrary. And W is given by this Faddeev logarithm with Q1 minus Q2 plus P2 E minus 2 pi I P1 Q2. So we have we are in L2 of R squared, so we have two copies of Heisenberg pair which carry indices 1 and 2. And phi b, the only difference with Ray's talk that phi b differs by inversion. So it's an exponential of 1/4, not minus 1/4. But otherwise it's the same. E minus 2i f of x. 2i x to z sinch b z sinch b inverse z dz over z. So that's explicit data. And so the whole information about the theory is completely contained in these two operators. And even more, the whole theory is concentrated in three properties of those operators.
Algebra. Any of these operators, or the quantum logarithm, there is operators.
Yes, but in the spectral sense. So, this is to define a function on an operator. It suffices to define suffices that the function is defined on its spectrum. But the spectrum of this linear combination is the real one. So it suffices that phi b is well defined on the real line, and it is actually takes values on the unit circle when this argument is real. So this is unitary operator for that reason. Algebraic properties. And so algebraic properties are the following. So the first property, R power 3 is identity. And then the pentagon for W. W12, W23 equal W23, W13, W12. And the third property, so if we take R1, P12, then this will be the same as some zeta W. P is permutation, yes. P is permutation. W R1, R1, W12, W12. And here zeta is a phase factor, which has explicit form E minus pi I over 12, B squared plus B minus 2 minus 4 alpha squared. Is that? No, plus. And if somebody of you have seen already those formulas, then here I add one little extra piece given by parameter alpha, and the reason is that as you see, the projective factor which comes from parameter zeta is affected by this alpha. And not using arbitrary b. B is supposed to be real in this case.
Sorry, is B another free parameter like alpha?
Both are free. Both are free. But let us take them real. But B also can be on the unit circle. The representation still will be unitary. But if B is real, but take any B. And then we can adjust alpha the way that zeta will be trivial. Right? So we just kill the fractional part times 12. So by choosing playing with alpha, we always can make zeta trivial. And this corresponds to the fact that the representation of the mapping class group of punctured surfaces in the quantum Teichmüller theory will be not projective, but true representations. And this feature is so the theory is 19 years old, and this alpha is a relatively recent observation dating back 4 years or so. And this opens the possibility that we deal with not just projective representation, which makes a headache with the phases of partition functions, but as you see, it becomes very almost in trivial way. It's a little modification, but still it affects the projective factor. Yeah, so that's input. And then how this works. How this works. And it works the following way. So just think of ideal triangulations. This is the first thing. Second thing, mark corners. And third thing, linear order on triangles. So you put all these three into the same at the same time, and then what you get, you get a surface of, but this time it should be punctured. So I need at least one puncture. such that S is positive and 2G minus 2 plus S is positive also. So the two conditions. And if you think in non-geometric way, this condition just make sure that the triangulations exist with vertices and punctures. So if there are no punctures, no vertices, so no triangulations. But on the sphere, if when you put one point, you cannot imagine any triangulation having this point as a vertex. But starting with 3 points on the sphere, you can imagine a triangulation. And for higher genus, it suffices just one puncture, and you can imagine the triangulation. Okay, so that's what we take. Then we triangulate, and then so linear order, Mark corner. Here is a typical triangle in the triangulation. And then when you change your corner like this, you just think of operator Ri. So this elementary change should be accompanied by appearance of operator Ri, and then if you do it 3 times, then the first property makes sure that you are consistent. And then you take a quadrilateral and think of this configuration Ij, and then think of making a flip. Then just think of Wij. And if you make a permutation of indices, then think of Pij. So permutation operator comes granted, so we don't need to even talk about permutation. And get representation of mapping class group of sigma in L2 of number of triangles. So that's a quantum Teichmüller theory, and then we can try to see if we can calculate something. Trying to calculate. And as my title contains the surface bundles, so what we are trying, we will try now. We will try to realize monodromies. And the typical geometric setting is to take a fiber knot, which gets a monodromy, and then we should try to realize its monodromy and see if we can make sense of its trace. But all these operators are unitary, so we are in the context of the question in the beginning. And let us take a trefoil knot. But maybe let me just take a surface of the type 1-1, which Ray just discussed, the punctured torus. Then the mapping class group, again, SL to Z. So it suffices to give 2 operators, and the rho QT, so quantum Teichmüller of T, becomes just W12. So we have 2 triangles, and so we get this, and on S we get what we get. We get W12 R1 R2 inverse. And so the claim is that all properties of the presentation of the SL2Z group are satisfied. For example, if you try of ST, right? This has to be order 3 element in the SL2Z representation, but it is because it is given by product of order 3 elements, because W1 to cancels out immediately when you multiply, and then so we have at least one relation explicitly realized. But for example, the fact that S squared S power 4 should be identity, now it is some long calculation, but it uses just those three properties, nothing else. So as soon as you have a realization of that system, you have a representation of the netting algorithm, no matter what is the name.
For all choice of alpha? For all choice of alpha? Or just...
Yeah, the for all choices. No, but if zeta is not 1, then this is projective. So the all relations are satisfied up to multiplicative factors. And okay, so and now we can make the monodromy. So the trefoil knot. So monodromy is given by who knows the monodromy of the trefoil? It is this, or the 6th element, and rho t of phi, qt of phi is 3. Let me put 3 1. Is given by P12 R1 minus 1. Okay, that's the monodromy, and then you just got to try to calculate the trace, but the operator is very explicit, so I leave you as an exercise to try it at home if it makes sense. Not because I'm always I almost don't have time, so let me just say a few words about a less trivial case of figure 8 knot.
What's the answer?
Here answer, so the trace of phi is finite, up to phase is 1 over square root of 3. Trace of square is still the same. Trace of cube is infinity. Trace of fourth power is 1 over 3, I think. Or maybe, so there is 6 values, right? It is a periodic thing. 1 over square root of 3, twice maybe, once 1 over 3. And twice infinity, something like this. Okay, which is in agreement with the Teichmüller TQFT, where you make you calculate it in well-defined way by switching dihedral angles, making everything absolutely convergent, and then taking off in the limit. And this corresponds to a regularization, a specific regularization of those traces. Okay, so what happens with figure 8? So 5 4 1 is 2 1 1 1. Yes, yeah, exactly, and rho qt of phi for 1 is simple thing. R1 W21 minus 1, R2 W12 R2 minus 1, R1 minus 1. That's the thing, and then if we try to calculate its trace, and you can guess that the answer is finite, and this is a state integral invariant, which first was written by Hikami, but not in this form. This is Hikami had some extra exterior variables which corresponding to peripheral data, but this corresponds to complete hyperbolic structure, so there is no any parameter. And so you see, it's in the integrand you have a pure phase, right? So this lives on the unit circle. This as well. So this integral does not converge absolutely, but by slight shift of the contour in the complex plane, it becomes absolutely convergent. So it is just improper integral and very well defined with a well defined answer. And in particular, for this quantity, you can just prove that there is a corresponding version of the volume conjecture that that if you denote this by z of for 1, zb, and log of zb of for 1 absolute value limit when b goes to 0, 2 pi b squared is minus volume of figure 8 knot, and which is equivalent to saying that dB of for 1 behaves like E minus 1 over 2 pi b squared volume. And again, we observe the exponential decay because the theory is unitary, rather than the exponential growth as we know for colored Jones polynomial. And this is a general conjecture that states that if phi is Pseudo-Nosov, then limit 2 pi b squared log of zb of okay, so trace of qt of phi when b goes to 0 is minus a volume of the mapping cylinder how it is called, m of pi, right? And in particular, if this conjecture is true, so that make we can be sure that for any such phi, the trace is a well-defined quantity. So we have infinitely many unitary operators with perfectly well-defined traces. So in particular, the general answer is expected to contain a sufficient essential enlargement of the domain of the definition of the space function. Thank you very much.
Any question or comment?
So the trace, if you compute it, is it always going to be a state integral?
Yeah, of course. You take the integral kernel, and that is it.
Coming back to the illustrative example, you said that this group, you wrote generate an exponential to pi I alpha p squared and q squared. I'd like to know the trace of these operators.
They are infinite. Infinite, yeah.
Oh, sorry.
Not everybody, everything is trace.
I see. Mm-hmm.
But if you take product of two such, then it is finite already.
Oh, I see. Thank you.
Any other question or comment? Okay, let's thank the speaker again.